Hello class, we're on our last type of optimization model for the prescriptive module of the analytics class. And so this model is the most difficult of what we have covered so far. And it's called nonlinear programming, NLP. And the reason it's difficult is the objective function or the constraint may be nonlinear, and that makes the problem not even guarantee an optimal solution. So there is no guarantee that the algorithm will give you the best solution, and we'll talk about that. The algorithm for LP, for IP guaranteed, and the binary guaranteed an optimal solution, but for NLP, there is only a best estimate using the algorithm and solver. So there are other things you can do to improve the solution, but it's still ways better than trying to guess it, or there isn't even a graphical way to find the optimal solution unless you just have two variables. And so the model I chose is called the pricing models because that's, again, a very common business problem. You're coming up with a product, there is competition, a new product or a service. How much should you price it? What's a price tag on it? We know that as the price increases, the demand, customers may go somewhere else and pick the product from your competition. So the pricing problem, yes, it exists for brand new products, but it's much more challenging when there is competition and you're trying to beat the 5, 6 other products in the market. And so it's a very common problem. Unfortunately, it's a nonlinear problem. And even these models are used because they give you much better solution than guesswork or trying to do any other type of analysis. And so they have their assumptions like all the other problems we looked at. And so we're looking at what the givens are. Usually the company wants to make a new product or deliver a new service. The market is very competitive. The inputs will be the demand, the price, combination. And so it's demand and price. Even if it is a new product, you can get data from the market, consumer sources that shows what the demand for a certain product was and at what price was it being sold. It's going to require a lot of data mining, but that's our job, is not just to do the models, to make sure that we're getting the right data in the right format, at the right time. It's going to require a lot of skills. If we're not the ones as analysts getting that data, whoever in IT or whoever owns the data, make sure we have access to it in order to build our models. Because otherwise, if you don't have accurate data, it's garbage in, garbage out. So you want to make sure that the data you're getting is accurate and makes sense. Or it doesn't matter if you build the best model in the world as an analyst. If the data is bad, the results will be bad. So the decision variable, what I'm trying to decide is the price. How much should I price this product for? Objective is maximizing the profits. And the constraint, we have very simple constraint here. We want to make it, the price, to be greater than the cost. We know how much it's going to cost us to make. We just want to make sure that the price tag we put on this should be larger than the cost. And so even in more complex models where we have bundling going on, this is more fancy model than this basic model, where we have bundling going on. You go buy a hamburger and they make it cheaper if you buy it with fries and the Coke. And so, so they may lose money on the hamburger, And these complementary products, that's where they make their money. They're not making money on a $1.99 hamburger. They're making their money on the fries and the drink. And so you may relax the price over the cost for the hamburger, but then overcharge for the fries and the Coke. And so that's the constraints here. And so let's look at this and what makes it nonlinear. This is a great example of utility company that is trying to come up with a price. Same with the oil companies. I mean, these oil companies use very sophisticated mathematical models to come up with what the oil price should be, what is the electricity price should be. We know that the price varies and the demand varies between on-peak and off-peak seasons. When we get the 100-degree weather, I mean, more people are going to turn their air condition on, and that puts a demand constraint on the network. And so same with IT applications, demand on the server time, on the internet time, and so on. So we know we have on-peak time and off-peak, on-peak price and off-peak price, but we also have on-peak demand and off-peak demand that, the demand is related to the price. And so the demand is a linear function. So there is a constant value, an on-peak price, and an off-peak price. So let's say this is peak price. So this is peak. We'll call it P. And this is off-peak. So this is O. O. So what does this mean? It means the demand function, big D, is going to be 2.253 minus 0.013 P times P plus 0.003 times O. And similarly, the off-peak demand is a different formula. These formulas are given as mathematical formulas in your book. But we don't care about the mathematical formulas. We care how to model it in a spreadsheet, and this is the best way to model it in a spreadsheet. And so you're going to tell me, so this is linear. What makes it nonlinear? It's when we calculate the demand, which is going to be the price multiplied by the price, which we're going to guess multiplied by the demand, then that's what makes it nonlinear. We're multiplying the price twice, so that makes it price squared. And so that's assuming the demand has an inverse relationship with the price. As the price goes up, the demand goes down. As the price goes down, the demand goes up. And so that's the key assumption here. And so there is an interesting twist. Another one on this one, which is very realistic, is, of course, the cost for capacity. We know what it is. The capacity is going to cost you the same regardless whether you have on-peak or off-peak demand. It doesn't care. Similarly, the capacity doesn't care. It's shared capacity. Again, doesn't know if the demand is coming from off-peak or on-peak. I mean, there are people who will keep their temperature at 62 regardless, what the cost is. Whereas there are people who budget and say, yeah, we're going to increase the temperature, turn the air condition off, whatever, so as we're not charged an arm and a leg. Capacity is going to be shared by the company between the on-peak and the off-peak demand. And so this is the interesting thing, is this problem has two sets of decision variables. This is the one problem where you cannot have just one set of decision variables like we've seen before. We have how much should we price on-peak demand, how much should we price off-peak demand, but also how much capacity should we plan for. And so that is only known after we know the demand. And so the demand is what will give us what capacity is needed. Otherwise, we don't source it from certain vendors. And so this is the first example where you see not only is it nonlinear, but it's also two sets of decision variables, which we can do in Solver. We just have to separate them by comma. And so going through this problem, the on-peak demand is B6 plus the sum product of the prices C6 to D6. So what's in B6? B6 is the constant plus it's basically these two numbers multiplied the price multiplied by the demand, the on-peak demand. Same here. This is the price, how much should I price it, multiplied by these two numbers, plus the constant. And so that's a sum product. So B6 plus sum product prices, this pink, comma C6 to D6, and this will be B7 plus sum product prices, C7 to D7. Okay, that takes care of the demand. And this is going to be the capacity. What is the capacity? We don't know. We don't know until we don't want to buy too much capacity, and then it turns that the demand is not there. And so we want to make that a variable, but then we put a constraint that the demand is less than the capacity. And so that gets captured in the model. And so the revenue is going to be the sum product, the demand multiplied by the prices. So these are the prices, and these are the demands. And so that gives us the revenue, how much we cash from the customers. The cost of capacity is going to be the 75 multiplied by this. So that's capacity times B9 times the capacity. And the profit is going to be my revenue minus the cost of the capacity. I mean, that way, the company is not overbuying capacity and to get ready for the demand. And it's pricing the on-peak capacity and the off-peak capacity well. This is an amazing application with so many areas it can be applied to, where you're not increasing your cost, and at the same time, you're guessing how much to price it for two types of demand even, not one type of demand. And this is why I wanted to cover it. This is back to the data table for spreadsheet models. And so you can see that I had to set it up for on-peak price. So if the on-peak price is 80, then the profit will be 97. If the on-peak demand is 85, this is the profit. So one variable, and it shows us because we can't do two variables, and it gives us a shape of the distribution. But that's very difficult to do with nonlinear functions. So unless you're dealing with one variable and can model it like this, you can guess if the objective function is concave or convex, and that's easy to guess the optimal solution. So let's look at Solver, how Solver was set up, data Solver. And so the profit is my objective function. Of course, I want to maximize it. And this is where I'm putting two sets of decision variables, separating them by comma. And so unlike Solver table, where I have to hold down the control key, in Solver, I think you can just type the comma. So you highlight this, then you put comma, then highlight the capacity. So again, this is trial. If it doesn't work to put a comma, guess what you're going to do? You're going to hold down the control key and then highlight capacity. Here is the constraint. The demands is less than or equal to the common capacity. And so here's the demand. These two numbers, the on-peak and the off-peak demand, is less than or equal to the capacity we need to have in the on-peak period and the off-peak period. And that's in under our discretion. When do we generally say on-peak time is and when is the off-peak time? Same with parking, right? Early bird pricing versus you come later. And the capacity, but then you may have fixed capacity in parking situations, so it'll be a bit easier. Still, you need to add the non-negativity constraint, and this is, I cannot emphasize this enough. This is the first model where we use a different algorithm. It's called GRG nonlinear. You don't select this GRG nonlinear and by default, you just go select the simplex LP. It's not gonna work, okay? You're gonna get maybe a solution, but it's not a good solution. And so we select that, we say solve, and it solves it and comes back with the best price we should charge for on-peak and the best price we should charge for off-peak. Obviously, it knew to make the price of the off-peak cheaper, and this is the capacity. I mean, this is amazing. So you're not exceeding the capacity. The total demand is not exceeding the capacity. You're not buying more than you need. You're not sourcing less than you need. And so it solved two problems in one optimal model, and you make a profit of 95, if this is $95,000 or whatever the unit is. And so an amazing application. You'll blow anybody's mind off with this application in business, because I can guarantee you, yeah, they may have heard of maybe LP model or something, but not an LP model with this magnitude of complexity. And so I wanted to end these optimization models, these prescriptive models, with a bang and give you a really nice application that I think you'll end up using it in real life. And so this can also be customized to different applications, and so you can use different demand functions. There's a lot of complexity that can be introduced in any of these models that we covered, and that's where the beauty is in that. And so you have the basic models now down, and you can expand on it with any real life application. So thank you, and that's the end of my optimization models.